So, yesterday we started talking about accelerator observers in Minkowski space, and so I have written down some formula here which I will explain. So, let me just write down one more formula to connect up, which is if I can find it. Okay, here we are. So, the family of accelerated observers was given by I'll write sometimes Cosh and sometimes just CH out of laziness. So these will be the family of observers on the right side of this. This right-sided hyperbolas will be these, and similarly there will be left-sided hyperbolas with minus signs. Here of with x negative. I'll write all of that. So it's better to use light cone coordinates. So now eta, as I mentioned, okay, counts time, okay, along the trajectory of the hyperbolic trajectories. So it's a time for these accelerated observers, and so this relation can be written rather more succinctly in terms of light cone variables for both x and t and eta and xi. Okay, and remember the acceleration, the magnitude of the acceleration along this was given by along any of the constant xi trajectories. The acceleration was constant, and it was given by this formula. Okay, all right. So in terms of the light cone variables, which are defined as so, okay, so my convention always will be that u will run at 45 degrees. So u will run towards top left and v will run towards top right. And the same thing is true about small u and small v. Okay. Now that is to say, it will be given by. So, but let me make one important. Well, actually, I take that comment back here. So, small u and small v will be given by eta minus xi and eta plus xi respectively. But there is one interesting thing about the. Okay, so this is how the story is in the right for the right-sided observers. On the right, this is the region I'll call R. I think Subrat has called it 1, and then so there will be similarly there will be observers which can see only the left quadrant. Okay, and for them the transformation between the capital UV and the small uv will be given by just the flipping the signs minuses. So for u, this minus will become plus, and for v, this plus will become minus. Okay, this is how this will go. And with this, you can easily see that eta runs upward. Okay, eta is future directed on the right. Okay, and with the same definition of eta as in here, that eta is past directed on the left. Okay, that's an exercise left for you. It's an easy exercise, but this is the direction of eta here on the right and here on the left. As a result, okay, now let me talk about field modes. which are constructed by the Rindler. So this is called Rindler space-time. Okay, so let me now write down the metric in this xi eta coordinates. So the metric in the Minkowski coordinate, of course, is this, which is the same as minus du dv, and that's the same as, now it's a trivial exercise, so apply this transformation, and that turns out to be e to the power 2a xi small du dv. So this is a situation that is there on the right as well as on the left, okay, and the sign flips in the future and past. In the future and past, there are no; these are not real observers; they're just space-like trajectories. Okay, so the hyperbolas that you might construct there. Okay, all right, good. So this is the this space-time, okay, written in this fashion where xi can be understood as a function of small u and small v. Clearly, it's just 2 xi is equal to whatever it is, v minus u. So that gives you the space-time. That's called Rindler space-time, and again, it's a conformal factor. So now let us talk about massless scalar field theory, again for convenience. Okay, for massless scalar field theory, the action in terms of Minkowski, it is just okay, in Minkowski coordinates it's like that, and in Rindler coordinates is the same. Okay. So clearly you can write down the solutions. The solutions are Minkowski-like solutions even in Rindler space-time. Okay, and so it will be given by. So first of all, I have rewritten the solutions, okay, of two-dimensional Minkowski space here. Okay, so I have dropped this, 1 over square root of 2 omega, etc., etc. These normalization factors you can put in. So it's proportional to exponential of minus. So recall that capital U and V are given by this. So I have written here only the positive frequency modes. Throughout here, I'm writing only the positive frequency modes. The negative frequency modes will be given by the bar, the complex conjugate of these functions. So note that I must ensure that minus omega must multiply the future sense of the time. Okay. So V has plus t in it, U has plus t in it, so this is correct. So exponential of minus I omega t, small t. Okay. So this is indeed positive energy measured with respect to the future time, small t, okay, in Minkowski. So these are the correct definition of the Minkowski modes. Let us look at now the Rindler modes. Can everybody see thing? Okay, so they can see it on the screen, I guess. So on the right, okay, on the right, exponential of minus I omega little v has the same feature that it minus I omega multiplies eta. Okay, so that's positive frequency. Similarly, minus I omega u, so minus I omega again multiplies eta, so that's positive frequency. I have extended the definition of these functions, okay, throughout space-time, also to the left, by simply saying, let me imagine that these are functions of capital V actually, by using the but I will say that these are some things which are positive, non-zero, okay, for capital V equal to positive. So, and I'll define these functions, okay, I'll extend these functions, this BR omega mode also to the left by saying that it is 0. Okay. Similarly, I'll define left modes which I'll extend to the right by saying that it is 0 on the right. Okay. So that's what this theta function, the step functions are doing here. And but note interestingly that on the left, okay, it's e to the power plus I omega little v. This is very important. Why have I chosen this convention is because now I omega is multiplying eta, but eta is past directed. Okay. So instead of choosing minus I omega eta, so I should always multiply minus I omega with the future directed time, whatever that is. So here minus eta is the future directed guy. So I have taken this to be I omega v. Okay, good. All right. So with this now, let us define the Rindler vacuum and the let us define the Rindler vacuum. So Sandeep, this will have to stay. I can. Okay, good. Right. So let me define the Rindler vacuum, of course, as what we said here. So the Minkowski vacuum, which we have already defined. Okay. So let me introduce the mode expansions. So according to Minkowski, I will have. Okay. Also, note one more thing that this V guys, okay, the Minkowski V guys, these are actually moving, okay, on the left. Okay, these are left moving modes and these are right moving modes. How do you know that? Because this multiplies t plus x. Okay, so as t increases, in order to keep the same phase, x decreases. So these are left moving modes, these are right moving modes. So same thing is true also for this v and u. The small v guys, you can convince yourself that the small v guys, okay, they are actually left moving globally, left moving in the global sense. Okay, and left moving is not the same thing as positive momentum measured by zeta, because on the left, you know, it's like a mirror world. Everything is different. So the xi momentum, okay, positive, okay, actually means that it's left here because the value of xi increasing towards the left. So it's a little funny thing, but you should make sure that the tilde fellows are all right moving and the untilde fellows are all left moving, okay, in the Minkowski sense. Good. So with this, we can now write down the oscillators. Oscillators will be denoted by small letters and the mode functions will be denoted by capital letters. Okay, and and they are complex conjugates. Okay, this would be the full mode expansion for the scalar field phi in terms of the Minkowski modes, and here I have to write a little bit more. So it will be like B omega r plus the small fellows on the left plus their complex conjugates, which I'm not writing. Okay, so I'll define Minkowski vacuum to be the one that is annihilated by the small a modes okay, and I'll define obviously the Rindler modes. Rindler vacuum as the one that is annihilated by this lot, all the B's, LR and tilde LR. Okay, that's the Rindler vacuum. And let's try to now find the relation between these. Okay. No, no, no. So now, okay, good point. So remember that I have made this thing into a global object. Okay, these are extensions of the modes that would have been. So I should probably use something for the mode just e to the power minus I omega v as set up by the right quadrant. Okay, now I have extended, however, by multiplying this theta of v by making them into global modes. So each of these guys have become a global mode. Okay, so there's actually an expansion throughout. Both of them. Okay, good. But only one set. Okay, just like the right-handed fellows cannot. They are not a complete set. Okay, I need both sets here because these fellows are all 0 on the left, and these fellows are all 0 on the right. So therefore, I need both of them. Okay, in order to form a complete set on any slice that runs through space-time. Okay. So now you can find out the following things that so clearly you can compare these two mode expansions on any given time slice in space time, and you will obtain the following you will obtain the following thing, that that A is a linear combination of so let me tell you forthwith that there will be this beta Bogoliubov coefficients here. Okay, and as I indicated that in case of non-inertial observers, okay, there is no reason why the vacuum constructed by them should be the same as the vacuum constructed by the inertial observers. So there will be these guys, and okay, so if you write B in terms of A, then this bar does not appear, but A in terms of B does have them. And so I'm just skipping a few steps here, but I'll explain what these alpha beta coefficients are to be computed. Okay, so you can get by comparing these mode expansions, these things where sorry, and similarly the thing for the tildes you can get similarly. Where these guys are simply okay. So I should write the inverse. I should write the inverse transformation. This is how I had originally defined the Bogoliubov coefficients, is that Br of omega. Let me write Br of omega as a function of V by using the transformation between V and small v and capital V on the right. Okay, if you do, you will find that it's written as a function here of small v, but let me write this. So this can be Fourier transformed. Okay. So this fellows can be written as the following Fourier transforms. Okay. Normally, Fourier transforms are written with a range minus infinity to plus infinity. I have simply split them here so that I can identify this object as a omega prime and this object as a omega prime bar. Okay. So it's the Fourier transform coefficients with omega prime positive that are alpha, and compute this guy suppose and simply make a change. Suppose you have computed alpha coefficients, okay, by doing this Fourier transform, okay, and doing the inverse Fourier transform, and then all you have to do is to get the beta coefficient is to change in this omega prime going to minus omega prime. Okay, but there will be branch cuts here, okay, in this expression. So as a result, taking omega prime to minus omega prime, like for example, if you have a square root, okay, it will have ambiguities. So that ambiguity has to be fixed by appealing to proper analyticity conditions. So you could do all that. But that's not the route that I will take here. I'll take some route which is a little more illuminating, besides being clever. So, but let us first tell you a little interesting puzzle, which is that suppose you have constructed these alpha and beta coefficients. After all, is just Fourier transforms, and in fact, you can indeed give this to Mathematica, and Mathematica does it correctly. And here you have, so in order to find the alpha coefficients, you have to multiply this expression by e to the power minus I omega v and integrate over v, right? Sorry, plus I omega prime v and integrate over v. So this has an exponential and a power, so it will be a gamma function. Okay, with appropriate scaling of things, it will be a gamma function. Of course, the contour here will not be 0 to infinity; it will be complex. Okay, the complex plane. You have to rotate it, and that will give you conditions and so on. That all comes out by Mathematica. It gives you those conditions also. So anyway, suppose you have done that. Now, Minkowski vacuum is given by A omega acting on this state equal to 0. So therefore, this entire bunch, this guy acting on the Minkowski space equal to 0. Okay, it's inadequate to solve, okay, for this state 0, okay, in terms of the Rindler oscillators. Okay, so suppose I write that equation. So by these, you can now show that is some linear combination of the Br omega and some alphas here, some betas here, Br dagger omega plus, these are independent oscillators, again some alphas and some betas of and this is equal to, okay. In fact, there is a similar relation also for the tildes. That's the second equation. This equation by itself is too little, okay, to solve for the 0 of m. Okay, so what's happening is that two sets of oscillators, okay, with their complex conjugates are being mapped into one guy. Okay, so there are two sets of B's and not two sets of A's. Okay, as a result, this thought of this as a differential equation, it looks a little bit like this. Okay, it looks like if you go to a representation in which the BR dagger is represented by X and BL dagger is represented by Y. Okay, and think of this as there is a representation like that, okay, in which the BR is ddx and BL is ddy. So this gives you some expression, something like x plus ddx plus y plus ddy psi of xy equal to 0. You can't solve for psi of xy from this. Okay. So, but of course, what turns out is that you can indeed split these A's, okay, into two sets. Okay, so that you have not just one equation like this, but you have two equations, and you have enough equations to solve for this. Okay, so this comment may not be completely understood at the moment, but let me carry on, construct two sets, and then you will see that I can indeed, at this moment, okay, this has unambiguous solutions. This has many solutions in terms of the B oscillations, because I have not given you enough conditions. Okay, I'll have two sets of conditions soon coming up. Okay.
A omega acting on 0 n is a unique, I mean, it will give me unique solution for m, right? 0 m.
Yeah, so what happens is that these A's, okay, will be can be split into two sets of A's. Okay, so that now it becomes like a square. So right now, the relation between A's and B's look like a rectangular matrix. Okay, I have to split the A's into two different sets. Okay, so that it looks like a square matrix. And then the going back and forth between the Minkowski modes and the Rindler modes, okay, becomes easier. Right now, okay, it doesn't. It looks like a rectangular matrix. It's basically splitting things like into sines and cosines. Okay, that kind of object. Okay, so so I'm not sure whether this particular thing was quite illuminating, but let me go on. And yeah.
Sir, if we split, if for small a, and for capital A, we split the integral in 0 to infinity and 0 to minus infinity, then shouldn't we get the result? And over here, the mismatch is because
You mean?
in the capital A, we are integral from minus infinity to infinity.
Yeah.
For B's, we are restricting to 0 to infinity integrals.
Yeah.
So if for the A ones also, if we split the integral into 0 infinity and minus infinity,
That's a good idea, but then they don't satisfy Klein-Gordon equation. If you use a discontinuity at u equal to 0, then it doesn't satisfy Klein-Gordon equation. E to the power minus I omega capital U with a theta of capital U, okay, written in terms of if you write the thing, then it doesn't. So we don't want to do that quite, but the idea is good. Okay, that's the kind of thing that we will. That's the kind of thing that we will use two sets, but not quite along the terms that you have said. Okay, very good. So what we do is just the following. This was a trick which was introduced by Unruh back in the late 70s or maybe early 80s, and is the following: that can we make, so this solution as it is, okay, is also is not analytic, okay, as such in the Minkowski coordinates. Okay, can we make this solution analytic? Okay, so that it's an analytic function through the entire V plane. Okay. Okay, let me take it back. Can we make this analytic in the lower half plane of the complex V plane. Okay. So first of all, we want to make this, okay, a smooth function for real V. But we want to be a little more ambitious, that we want to make it also analytic in a large part of the complex plane, namely the lower half part. Why lower half? Because look at the behavior of this Minkowski mode, this, okay, and omega is positive. This is analytic in the lower half plane. Okay. In particular, put V equal to minus I infinity, you will get 0, which is a good answer. In the upper half plane, however, you put V equal to plus I infinity, that will give you an infinity, so it's not analytic in the upper half plane. So let us demand, let us try to take this function, okay, and see how this function looks like, okay, when it is continued to the entire complex V plane, so that it's analytic in the lower half plane of V. So the answer is the following. So this is analytic in the lower half plane of V. So that's an observation. And now I claim when it is made analytic in the it is the following. It of course looks like B r omega on the positive segment of the, so it looks like this for so this basically means that when I rotate this in the complex plane, okay, so let me write down. So this looks like the old function, and it looks like pi omega a So in order to make it analytic in the lower half plane, what you have to do is to rotate this guy, okay, by applying an e to the power I pi here, okay, in order to go to the, so this is how it goes. Okay, let me leave this as an exercise, okay, and sorry. This is the result. Okay, so by combining using the global, okay, so I can in fact combine this. So what I'm trying to say is that basically when you go to minus V, you want to compute a thing like this, okay, minus AV to the power I omega A. Okay, how are you going to interpret this minus? Are you going to interpret minus as e to the power pi I or e to the power minus pi I? Okay, so if you want something to be analytic, think of going to minus like this. Okay, that's e to the power minus pi I. Okay, so once you do that, you will find that this object should be interpreted as e to the power. So this fellow here is e to the power minus I pi So this should be interpreted as e to the power pi omega a times AV I omega a. Okay. So the analytic continuation looks like e to the power pi omega a times AV to the power I omega a. Now let us see what. So this analytic continuation is precisely what BL omega bar is. If you look at the expressions, BL omega bar is precisely that. Okay, this you should find from the expressions that are given. That remember that BL omega has e to the power I omega v. When you take the complex conjugate, it becomes e to the power minus I omega v. Okay, so so I get that e to the power minus I omega v written in the Minkowski coordinates, okay, is pi e to the power pi omega. So there is a relative factor between r omega, the continued Br omega, and Bl omega bar. That's the factor of e to the power pi omega a. It comes by carefully choosing an interpretation of the minus sign. I can tell you in the discussion a little bit more about this one, but anyway, that gives you this feature that the analytic continuation of this function AV to the power I omega a, okay, it's Br omega on the positive V axis and e to the power minus pi omega Bl omega in the relative factor between this and this I have just derived over here. Okay, so as a result, I get this new mode which I will call Fr omega, which is Br omega plus e to the power minus pi omega a. Imagined in this expression that I have stuck these factors of thetas in these, and Bl omega bar. It's very important to note that this has played a role in this thing, that it is e to the power plus I omega v, which are the positive frequency modes, and it's e to the power minus I omega v, which are the negative frequency modes. Okay, so here we go. So this is now these guys, okay, are all analytic in the lower half plane of capital V. As a result, you know by construction that the Fourier transform of these fellows, okay, cannot involve e to the power. So this must be a linear combination of only these. Okay. So there will be no beta coefficients between this. Yeah, hi.
Singularity at 0.
No, so you can show that this fellow does have a branch point, okay, but that does not affect your taking the Fourier transform. Yeah, you can show the branch. So by this construction, the branch cut, however, has been sent to the upper half plane. Okay, so that's all that happens. That's an important point, but it doesn't. So this is a linear combination of only the positive frequency. So the linear combination of only the A omegas, and the A bar omegas do not appear in this this thing. So as a result, the mode decomposition, okay, of the scalar field in terms of these modes, okay, will define the Minkowski vacuum actually. Okay, so let me define. Okay, I'm running a bit slow. How am I doing in time, Sandeep? Okay. Right. Now that I think that's probably fine. Uh, so let me shuffle the mode expansions a little bit, in which I write these guys. So I had the original mode expansion in terms of the B modes and their complex conjugates. So now I'll just take a little bit from here and sort of combine them with the, so this B R omega, I'll combine that a little bit with the B L bar omega, etc., to arrive at a mode expansion which is this. And the tildes, okay, and the complex conjugates, okay, where because of this rearrangement, okay, so first of all, if I define it in terms of this F modes, as I have just said, that these guys will be indeed annihilated by this primed fellows. So this will be annihilated by this and the tildes, of course, also. Okay, where this rearrangement means that these oscillators will be some linear combination of these B's and B daggers, okay, and that linear combination is given as follows, that the old modes will be given by the new modes like this. Okay, so here I have defined just so far is just a notation. 2 pi by A. So I have, in other words, I have called this guy as the e to the power minus beta omega over 2, and that BR okay, with a normalization that you can easily find out from the normalization of beta functions of the Bogoliubov coefficients that I said last time. It's okay. If both have to satisfy the canonical commutation relations, then so and the inverse is that the B prime oscillators are given by these are all easy things to derive. I'm sorry. With the normalization, this factor of e to the power minus beta omega over 2 has to be split between these two guys. So I have some beta omega over 4 here. So I have some beta omega over 4 and BR omega. So this last equation which I'm writing is the most important one. Okay, this. So once again, let's go through the steps. So I have found a certain linear combinations of this A omega prime guys, okay, two sets of linear combinations, because there will be a similar story with the left. Okay, so now you see the right the right Rindler mode, okay, gets mixed with a little bit of the left Rindler mode. Okay, both of these are this untilde fellows. They are actually left moving. Okay, so the left moving Rindler mode on the right is getting mixed coefficient. Okay, I'm calling this Boltzmann suppressed because it's exponential, but it's actually turned out to be a Boltzmann suppression. Okay, with it gets paired. Okay, so this is how the picture goes. So remember, this is what our notation is, that these fellows are BR tildes, these are BR, and this is a colored chalk that would have been good. BL tilde, and this is BL, is BL. Okay. So what is happening is that you take a linear combination of this guy and a complex conjugate of this one. Okay. So it's taking a mixture of the particle here and an antiparticle here. Okay, with a factor of exponential of minus beta I omega over 2, and those become Minkowski modes. Okay, those are linear combinations of Minkowski modes. You do this for both the R and the L, so you get two sets of such modes. One is FR omega, another is FL omega, and their tildes. Okay, so with this admixture, you get this result that so now, because the primed oscillators are annihilating this vacuum, you can show that it is this combination, okay, that is annihilating so it is this combination. So you can take the relative factor of this there again. Okay. Now there are only two oscillators here, and there are similar equations with this one. This you can solve. Okay. Now we can solve for this state Minkowski vacuum entirely in terms of the Rindler modes acting on the Rindler vacuum. So use the same representation that I had said before, that think of this, okay, as so think of this as x, think of this as y. So the first equation becomes d dy minus and the second equation can somebody say what the solution of this equation is? Now I have two equations, okay, and I have this psi xy. So there is in fact now a unique solution. Okay, that unique solution is, this is the well-known representation. Okay, it's called Berman representation, coherent state representation, or what have you, in which the these A and A daggers are treated as position and momentum kind of thing, and so in terms of this, it is a constant times exponential of this factor x times y. Written back in terms of oscillators, we have found the result. So I'm interpreting this guy as a wave function of the B daggers. That's the idea. So this result, exactly this, gives me similarly with, so this happens for all the modes. So you put a sum over omegas, and similarly there are tilde terms. So this is what I had promised. This constant refers to the vacuum of the Rindler modes because they are annihilated by these derivatives. Okay, they are just so recall that Rindler mode clearly is represented by constant here because and d dx, this constant corresponds to the Rindler mode here. Anyway, you can prove this and you get result. Now it's a simple exercise to show that okay, so it's a simple exercise to show that this is the same as so let me just write E and E. This corresponds to the left oscillators and this corresponds to the right oscillators, and so this is over all states. Well, maybe this requires a little bit of proof. So let me just go over the proof just very quickly, maybe. So these are all states of L and R. Okay, these are all states of L, and in this, okay, write it slightly better. So this is an entangled pair of states in which, let me write it this way. These are created by the L oscillators and these are created by the R oscillators. But I take the same, okay, and it's the energy eigenstate of the energy eigenvalue of these states. So energy eigenstates, all energy eigenstates of L and the same energy eigenstates of I, okay, where I of L typically would look like BL dagger to the power n omega for all omega acting on 0, okay, and so R would look like the same n omega distribution So this is what you do. Okay. Normally, an arbitrary state will have NL omega here and NR omega here. The number of left oscillators that are excited and the number of right oscillators that are excited need not be equal. But here, what happens in this exponential when you bring down this? So, in order to prove this result, you have to bring down this result, and the value of EI. Okay, the value of EI E on these states will be given by the omega n L omega. So, this E is the E of a particular only the left side of the Hilbert space. Okay, so that will be given by sum over omega of NL omega, and that's the same as sum over, well, it's just given by this. Okay, it's just given by this. Okay, so that's, so the way to derive this is by bringing this down in the from the exponent and expanding it out, and you get. So basically, what I wanted to say is that the reason why this guy and this guy are the same is because they are paired equally every time. So in the Minkowski, so the Minkowski vacuum is a bath of Rindler oscillators in which the BR modes and the BL modes are all paired all the time, and the BR tilde modes and the BL tilde modes are paired all the time. So this pairing, as I said, is like this. If this is the horizon, then these two fellows are paired, okay, and these two fellows are paired. So these are contexts, they are called Hawking pairs. Okay, so this is how they are paired, and this is why the entanglement is of a particular kind in which the state of the left Hilbert space and the state of the right Hilbert space, as defined here, are the same states. Okay, they have the same quantum numbers, and not the same states, they have the same quantum numbers, and this is the usual expression for energy of a scalar field. Okay, it's like that. I'm probably running out of time already. So this state has, of course, a lot of history. This is okay. So yeah, maybe I'll take 10 more minutes or something. Is that okay? Okay, right. So yeah, good. Okay, so let's draw draw from this. So first of all, so even if you did not follow the switch from here to here, let me first make a simpler observation that okay, maybe I'll make that observation here first, is that the remember that we got this thing, that up to some normalization, the shuffled oscillators, which actually annihilate the Minkowski vacuum, up to some normalization, they are just given by Br omega minus and this annihilates the Minkowski vacuum. So this clearly, these guys up to overall factor, these guys are the beta coefficients. Okay, so you can, let me write actually the normalization. This is important in this one. The normalization is such that this thing, half of this comes here. Okay, and now you can compute in this thing, okay, what is the particle density of the Rindler modes. Okay, and there is a similar expression for this thing, for the L modes, which is the linear combination of these things. Okay, and that so let's compute this now. As I said, that it's the sum over beta square. So the beta coefficient is actually this. Okay, so you can write the similar expression here, and you can actually compute this. It's not a big deal. So it's a square of this. So is this divided by 2 sorry. And it's not difficult to see that is the same as e to the power beta omega minus 1. So that's the Planck distribution. Okay. So therefore, the Minkowski observer, the Minkowski vacuum looks like a Planckian distribution of Rindler particles. Okay. So you can, so this where beta we had defined just by fiat to be 2 pi over a, and this says that indeed that was the right thing to do, okay, because this beta now gets identified, it appears in the as the inverse temperature of the Planck distribution and Bose-Einstein distribution. This is a Bose-Einstein distribution, and okay. Yeah, so it is the right moving mode on the right, and the right moving mode which also these are entangled. These fellows are entangled. As you can see from here, this tilde. Okay, so in my thing, the tilde fellows. So I'm really looking for colored chalks. So this tilde guys, remember, are going like this. So let me write this. So these are Br tilde, and these are Bl tilde. Okay, these are entangled in this state. Okay. It's the same picture. That's right.
Those can be formed outside in the region 1, right?
So okay, so I'm not there in the black hole yet. So there is a mimicry of the collapsing black hole by the eternal black hole. Okay, in that the picture of the pair is exactly this. The entangled pair is exactly this. Okay, so okay, so I'm of course out of time. So tomorrow what I'll do is exactly where I was beginning to. Yeah. Okay, maybe I should just say how this here is. So suppose I ignore the tildes for the moment. Let me bring down this object. Okay, this exponential. If I expand the big exponential here, then it will be like n divided by like that. Yes, sorry. Omega over 2, and like that. Now, this, of course, what you can do is to split the factor of 1 over square n factorial into square roots. So, to be precise, this is what it is. So, let me write it like this. And e to the power minus sum over n. So, for any given omega, you can do this. You can use the summation symbol as instead of n omega, just to say that there will be similar things for other guys also. So, you will get a sum over n omega running from 0 to infinity, and like this, acting on the Rindler vacuum. So what does this do? Okay, it excites the BL oscillator in the omega mode, okay, n omega number of them, and the BR oscillator, okay, in the Rindler vacuum exactly by the same number n omega again. Okay, so that is why that the left modes and the right modes are paired. They have the same number. So entanglement is of that kind, okay, in which this quantum number and this quantum number are the same, because they come from the same thing here. And also note that I have now got exponential of minus n omega beyond. So this n omega, so let me write the beta over here and n omega. So this is nothing but the energy of the omega mode. Okay, it's multiplied by, so I'll interpret this n omega as the occupation number clearly. Okay, so it's the occupation number times the energy of the single particle energy. So that's the total energy of the system. So that is what appears here. So I interpret this and a sum over such things. So there's overall there's a product over all possible omegas. So this product here makes it into a sum over omegas, and that's what this energy is. Okay, so that is what it is. This is called the thermofield double. So tomorrow we will explain all these things in the black hole context, okay, in which I can hopefully go fast because the technology is here, and so I'm sorry I went a little slow, but I'll try to make up tomorrow.
Kind of short of time, but if there's one urgent question or two at most, let's take those and then go for lunch. Anybody? There is a discussion session also. There's one question, let's take that one and then.
Sir, the curve you drawn in the right side and left side, the trajectory, does it indicate the trajectory for the accelerated particle in Rindler space?
Yeah.
But it doesn't seem like that space-like region, it won't be violate causality.
I'm sorry, what?
Isn't the region is space-like? The right and left region.
No, these are all time-like normal observers, like a like an accelerated particle.
So the particle is of the time-like direction.
Yeah.
Okay, I thought that is in the space-like region. The trajectory is in this space-like region.
I mean, this is going in the future.
So that is along the 45-degree angle, or that in the.
No. These are all within there. So in each thing, you can. At this point, there will be a light cone like this.
Okay.
Within that light cone.